participate in this program and to talk about a joint project that we have with Ohridski about using the notion of Kalimullin pairs to get definability results and the structure of the enumeration degrees. So I'll start by outlining some definitions about enumeration reducibility, just to remind you. So a set A is enumeration reducible to a set B. If given any enumeration of the set B, we can come up effectively with an enumeration of the set A. And more formally, if there's a C set W such that A can be represented as the set of X's for which there is a U such that the pair XU is in the C set W, and the finite set with code U under the standard coding of finite sets is a subset of B. In this sense, C sets give rise to operators on sets, and they'll be called enumeration operators. And this reducibility reminds us of Turing reducibility, but in contrast to Turing reducibility, where we can use both positive and negative information from the oracle set B, so we get yes and no answers to membership questions, and obtain positive and negative information about the set A, enumeration reducibility just uses positive information for B and gives positive information about A. So the precise connection between the two reducibilities is given by this. A is Turing reducible to B if and only if A joined with the complement of A is enumeration reducible to B joined with the complement of B. Okay, so enumeration reducibility is a preorder on the subsets of the natural numbers, and as usual gives rise to a degree structure. The enumeration degree of a set A consists of all sets B such that A is both reducible to B and B is reducible to A, in which case we say that A is equivalent to B. And the enumeration degrees can be ordered in the standard way. There is a least element, and in the Turing case, the least element consists of all computable sets. Here, the least element consists of all computably enumerable sets. And we can define the least upper bound operation in the standard way. So we have an upper semilattice, and to get the complete analogy with the Turing degrees, we want to define a jump operation. Now, the set that initially comes to mind looks like this. Ka is the set of all x's such that x belongs to the x enumeration operator or the xc set applied to A. But if you just use this set, unfortunately, you'll get a set that's enumeration equivalent to A. So in order to get a jump that actually jumps up, you're going to have to use the complement of this set, because this is where the actual diagonalization takes place. So the enumeration jump of a set A is Ka joined with a complement of Ka, and this operation is degree theoretic. The enumeration jump of the degree of A is just the degree of its jump. Okay, so now we have an upper semilattice with jump operation, just like the Turing degrees are. And this fact that we observed right at the start actually uses an embedding of the Turing degrees into the enumeration degrees. So if you map the Turing degree of a set A to the enumeration degree of A joined with a complement of A, then you get an embedding which preserves the order, the least upper bound, and the jump operation. And the substructure, which consists of all images of Turing degrees under this embedding, is called substructure of the total degrees, and it's an isomorphic structure to the Turing degrees. Okay, now let's move on to K-pairs. The notion of Kalimullin pair was defined by Kalimullin. We call them K-pairs. He had a different name for them. And the definition is very simple. A pair of sets A and B is a K-pair if there is a C set W such that A times B is a subset of W, and the complement of A times the complement of B is a subset of the complement of W. Now you can get examples of K-pairs very easy if you take one of the sets to be C. For example, if U is C, then for every set A and U and A form K-pair. And the C set witnessing, for example, that A and U is a K-pair is just the Cartesian product of the set of natural numbers. and U, and that does the job. So these are not very interesting, and we'll call them trivial k-pairs. And as soon as you consider non-trivial k-pairs, you get some interesting properties. One property, which is going to be used later on, is that if A and B are a non-trivial k-pair, then A is enumeration reducible to the complement of B, and the complement of A is enumeration reducible to B join 0 prime. Now, just to get used to this definition, I'm going to prove the first property. So suppose A and B are a k-pair, and this is witnessed by the C set W. So A times B is a subset of W, and the complement of A times complement of B is a subset of the complement of W. Then, I claim that A is the set of all x's such that there is a y, such that xy is in W, and y is in the complement of B. Now, one inclusion of this is very easy, because if x and y is in W and y is in the complement of B, x has to be in A because of this property. Otherwise, we'll get a contradiction to this. So this is very easy to show. And to show the other direction, we have to show that for every x in A, there is a y in the complement of W, such that this holds. Well, suppose not. Suppose that x is such that for every y, if xy is in W, then y is not in the complement of B, y is in B. Well, now because of this property, we have that B can be defined as all y's such that xy is in W. So it turns out that B is a C set, but we were given a non-trivial k-pair, so this is again a contradiction. So this proves the other inclusion as well. And the second part of the property is proved in a similar way, but you use the complement of W, and that's why you need 0 prime. Okay, now in order for k-pairs to be useful for definability results, they need to be first order definable themselves. This was proved by Kalimullin. He showed that a pair sets A and B is a k-pair if and only if their degrees satisfy this formula, which essentially says that for every x which is not above A and B, A join X and B join X form a minimal pair above X. Okay, so now let me give you some examples of non-trivial k-pairs. Well, they come from Jokush's notion of a semi-recursive set. So a set of natural numbers, say, is semi-recursive if there is a total function, total computable function, which we call a selector function for A, such that it's defined on pairs of natural numbers. It always outputs one of its inputs. And if it happens that one of the arguments is in A and the other one is not, then the selector function will correctly pick the one that's in A. And if you have a semi-recursive set, then it's really easy to show that A and the complement of A is a k-pair, because the C set witnessing this is just going to be the set of x and y, such that the selector function on x and y outputs x. And Joku showed that there are semi-recursive sets that are not C and that are not co-C in every non-zero Turing degree. So this gives a lot of non-trivial k-pairs. And the third example, which is a special case of the second example, is the following. So let A be any set of natural numbers, and let left A consist of all finite binary strings which are to the left of the characteristic sequence of A. So if you imagine the full binary tree, where should we put it here? Then you'll have the characteristic function of A is just one branch in this tree, like this. So all finite binary strings that are to the left of it and along it, this is going to be left A. The complement of this set will be all the finite binary strings that are strictly to the right. That's why we call it right A. And left A, right A is always a k-pair because left A is semi-recursive, and the function, the selector function for left A works as follows. Given two finite binary strings, it compares them and sees which one is to the left and outputs that one. So it plays it safe. And because this ordering is computable and linear, this is a total selector function. This third example turns out to be a significant example in terms of enumeration reducibility for the following reason. So for every set of natural numbers, we have that left A is always enumeration reducible to A, right A is almost always enumeration reducible to A, but they're not too far below because their join is still equal to the join of A and the complement of A. And it's a significant example because A is semi-recursive if and only if A is one reducible to left A. So if you're just interested in the enumeration degree of a semi-recursive set, you might as well think of it as in the form left A. Okay, so now let me illustrate how you can use k-pairs for other definability results, and I'll illustrate it on the definability of the enumeration jump. Now, as a comparison, let's see what the Turing case is. It's a theorem of Shor and Slayman that the Turing jump is first order definable in the Turing degrees, and their theorem consists of two parts. The first one is Slayman and Wooden's theorem that the double jump is first order definable. And then the second part shows that for every non-delta 2A, there is a G which joins A up to G double prime. And so using these two, 0 prime is the greatest degree which does not join any G to G double prime, because 0 prime join G would have to be less than or equal to G prime. And then relativizing, you get the definition of the Turing jump. So the first ingredient comes out of Slayman and Wooden's analysis of the automorphisms of the Turing degrees, and the definition of the double jump is in some sense hidden in it involves coding of second order arithmetic in the Turing degrees and translating facts about automorphisms into facts about definability. The second part is also really hard to prove, and it involves sharp analysis of Kumabe-Slayman forcing. Let's now look at the situation in the enumeration degrees. The definability of the enumeration jump is again proved by Kalimullin, but here I'll present a different definition of the enumeration jump. For one thing, because it gives a different insight into it, and secondly, because it's for the most part really easy to prove. So it comes out of this theorem. For every non-zero enumeration degree U prime is the largest among all least upper bounds A and B of non-trivial k-pairs AB such that A is below U. So you have U prime somewhere above, and then you're considering all k-pairs A and B such that 1/2 is below U. There are many possibilities. So what this theorem says that the least upper bounds of all of these is below U prime, but there is one which reaches U prime. Of course, this definition doesn't work for 0, but 0 prime can still be obtained from this because there are low degrees whose jump is 0 prime that are non-zero. Okay, so how do we prove this? Well, the first part is just one line. If you consider a non-trivial k-pair A and B such that A is below U, then by this property, we have that B has to be enumeration reducible to the complement of A, and the complement of A is enumeration reducible to the jump of A. So the join of A and B is below the jump of A, and by the monotonicity of the jump operation, the jump of A is below the jump of U. So half of it is already proved. Now for the second half, we need an example of a k-pair that joins up to U prime. Well, consider the k-pair that you get from left ku and right ku. So by this property, we have that left ku is always below ku, but ku was equivalent to u. So it fits the description so far. And then the join of left ku and right ku, again by this property, is exactly ku join the complement of ku, but this is exactly the definition of u prime. And we're done. Well, almost. The only thing that we haven't seen is that left ku and right ku is a non-trivial k-pair. So suppose that it's not. Suppose that it's a trivial k-pair. Well, what this means is that one of the sets left ku or right ku is CE, but then the other has to be at most pi 1. So their join, which is still the jump of u, can only be 0 prime. So u has to be low. And in this case, we're entering the realm of the local structure of the enumeration degrees. So the local structure consists of all degrees below 0 prime, or all sigma 2 enumeration degrees, containing or consisting entirely of sigma 2 sets. And our project was originally started in the local structure, and the first property that we proved is that for every delta 2 enumeration degree u, there is a k-pair AB such that A is below U and A join B is 0 prime. And now because if U is low, U is delta 2, this completes the solution of the previous theorem, the proof of the previous theorem. In the local structure, we also proved that k-pairs are first order definable, which was technically much more complex result, but it had very nice consequences. Because of it, we were able to characterize the first order theory of the local structure as computably isomorphic to first order arithmetic. And we also obtained the definability of some other classes of enumeration degrees, among which the class of low enumeration degrees, which was surprising because it is still open if the low Turing degrees are definable in the local structure of the Turing degrees. Okay, so this should hopefully convince you that k-pairs are useful for definability results. And now I'll move on to the problem that we hope to still find a solution to using the notion of a k-pair. So the goal is quite ambitious. It's the definability of the total degrees. And before I tell you what we know about that so far, let me try to motivate this problem. Well, first of all, if we could show that the total degrees are first order definable in the structure of the enumeration degrees, then we would have a definable copy of the Turing degrees in the enumeration degrees. Why is that good? Well, for one thing, it would solve a problem that has been open for a long time. You can find it in Rogers' book from 1967, but that's not a real reason. A more interesting reason is given by this. The total degrees are an automorphism base for the enumeration degrees. This follows from the theorem of Selman. And if we could prove that they are definable in the enumeration degrees, then we would have a definable automorphism base, which means that any non-trivial automorphism of the structure of the enumeration degrees would induce a non-trivial automorphism of the Turing degrees. And this would connect the automorphism problems for the two structures, which I think would give a different way of attacking the problem about automorphisms in the Turing degrees. Okay, so what do we know so far? Okay, so consider a non-trivial k-pair of the form A and the complement of A. We had many examples of these. The semi-recursive sets, this left and right, they're of this form. Now, using this property that we showed here, it follows that if you take another k pair, A and B, then B has to be reducible to the complement of A. And similarly, if B and the complement of A is another k pair, then B has to be reducible to the complement of A, which is A. So k pairs of this form are maximal in the sense that you can properly extend both on both sides to get a higher k pair. So call k pairs which have this property maximal k pairs. Now this is a property that's definable. And furthermore, Dżokosz's theorem about the existence of semi-recursive sets shows that every non-zero total set is an enumeration equivalent to the join of a maximal k pair. Now, for the most part, we saw this already because for sets for which the degree of A joined with a complement of A is not pi 0, 1, then A joined with a complement of A is the join of this maximal k pair. Dżokosz proves that this is true also for, in his setting, the CE Turing degrees, in our setting, the pi 1 enumeration degrees. Okay, in the local structure, we were able to show that the opposite is true as well. For every non-trivial sigma 2 k pair AB, there is a k pair of this form, C, and the complement of C, which extends it. So, as a corollary of this result, we have that in the local structure, a degree is total if and only if it's the least upper bound of a maximal k pair. And the question that we don't have an answer to is this true also for degrees that are not below 0 prime? Well, this is all I have to say.
Let's thank Maria once more.